Okay, so today we're going to be covering Lexing and tokenizing, and sort of how I implemented it in my interpreter or parser. Um, I took the naive approach because it's just a calculator, so it's going to be fast. Anyways, the expressions aren't going to be that long, and also I think it's pretty much O of one except for collecting numbers. Now, the way we're doing it is basically Lexing sounds more intimidating than it actually is. Same goes for tokenizing, except tokenizing sort of makes sense. So let's look at this sort of at this lexer type. So uh, yeah, so when we have a lexer is I haven't implemented it as maybe would be more optimally, but let's say we take our initial string here, so our expression string, and then the lexer sort of just has this sort of the string here, and it points to a place, and then it advances to it advances the pointer to the next character, and that's just basically what a lexer does. And then we tokenize based on what we get. So yeah. Now, why would we want to do this is one of the questions. Now, when we have this sort of computer, when we want our computer to recognize what a character does and things like that, we're gonna want it to give it the type of token. So we don't just have the character. We need the type and then give it some rules to like sort of evaluate this type. So here it starts with negative, then it's parentheses, then it's number, then it's a sum number, and then notice how it skips any white space. So yeah, we'll go through the code of how the lexer works. Now, what we do here first is we take the string provided as the first argument, and then shove it into the input of the lexer. Let's look at the lexer type to make it more clear. Whoops, wrong keybind. All right. So the lexer type here, it's a constant string, which is the input. Then it's a position, and it's the current character we're on. All right. So yeah, when we initialize it, we say that the input string is our expression. We set our position to 0, and then we set the current character to the expression to the first character. Yeah. We also have a predefined array of tokens and this length here. Now, this is not important. These parts are not important right now. They're more sort of important when you build the tree, which is what we'll cover in the next video. Okay, so once we set up our lexer to have our string and our position 0, you can actually shove it in this while loop and get the characters in sequential order, putting them in our array. So this is what we do at the get tokens. We pass the pointer of the lexer, and we sort of play around with that. So first, it checks if we're not at the end of the string. It also does that here. This also checks if it's not at the end of the string, but that's fine. Now we do that again. We check if we're not at the end of the string by checking if the current character we're on is not here. Then we set up a token type. Now let's look at what our token looks like. Our token is just gives us a type and contents. Now it can either be a name, which is like this sort of string, a 9-character string, double for the number, and and a character for the operation. All right. So here we first skip the white space and we advance the lexer. And advancing the lexer is actually pretty easy. Yeah, I mean we just increase the position and update the current character. Then we continue. Now now we check for numbers. So if our character is between 9 and 0, then we set the type to number, and then we collect digits, and this sets the return value for this is a number. So it takes in a lexer as the pointer again, a pointer to the lexer as the argument, and we start at the position. We set a start at the position and the number of periods we have here as 0. then it checks if we're between 9 and 0, or if it's a period, and if the number of periods does not exceed 0 or is equal to 0. So we can, because we can only have one period in our or decimal point in our numbers, so we can't have any more than that. All right, and then we advance Lexer, sort of collecting these in the Lexer, and then we look at the length. Pretty sure, yeah. We look at the length of the Lexer, which is just the position we're on minus the start we were in. And basically, so this is how it looks like. I think Shift F9 will clear. Now, our Lexer right now, there's a bunch of stuff. And then let's say we have 10.28, 0.281, that's it. And then there's more stuff here. Now, we stored this start, and then we kept going until we got to the end, or to the current position. So this is the start, and this is the position, right, that we got when we kept advancing. All right, then what we do is we malloc a string for string buffer, and then what we do here is we paste in what's between the start and the end position. All right, so now we have a buffer. Let's just say buff, and it equals this string 10.281. Grommet is kind of slow right now for some reason. Okay, and then we copy, so that's what the string copy does. And we also want to add a null terminator, because this doesn't have a null terminator. And then what we do finally is we convert this buffer into a number using the atof function that comes with math. I forgot which one. It either comes with math or string. So and that returns the double that was in between here, right? So let's go back to token here. Okay. Once we do that, after that we check if it is an operation, or sort of the parentheses. Even though parentheses aren't exactly operations, they're single characters tokens, so I kept it in the operations here. Now, so it's just a case, it's just a switch case, and where we advance the Lexer, we set the token type and the contents, and then we return the updated token. Now, the thing about switch statements is they're actually pretty darn fast. They depending on how they're set up, they can have O of 1 complexity if they build up something called the jump list. So yeah, sometimes you don't need. It's better to use a switch statement over a hash map, even if you're the enum you're going through is really long. Wait, no, that's not how hash maps work. But yeah. Switch statements are really fast. It's better to use them over if-else statements if you have, first of all, if you have a really long thing that's checking the same variable. Okay. Now, if it's not any of these, we return the symbol type, and we collect a word here. Now, I don't really care for this one. I haven't really implemented any symbol types correctly, so I'm not really going to go over this as much. It basically checks if it's not any of the other important characters, and it does something similar to what we did when we collected the number, but instead of that, we just collect normal characters, and it checks if it's shorter, if it's not as long as what we want it to be. All right. Okay. So now let's go back to main. Now that we know how we get the tokens. All right. Now notice how we never tokenized the negative sign in the get next token part. That's because it sort of depends on context. Because it uses the same character as the sum, as subtraction. So here what we do is we check the subtraction if our type is subtraction. Then we check if what is on the left side is not, if it's not a number. We should probably also check if it's out of we do check this. Right? And if that's the case, we change the type to negative, and then we add it to this other index here. Here this par ops and then current nesting Basically, instead of doing something weird like a prep parser, which I didn't wrap, I didn't get my head around it like when I watched the video first. Uh, Instead of doing something like that, I just collect it and then into different nesting levels and different types of operations. All in different arrays, and they get sorted automatically. But yeah, right now we finished. We sort of explained how Lexing and tokenizing works. Oh, I forgot to mention last video that I first got inspired to make this project because I saw Soding's video on making lambda calculus. So that sort of showed like he made that in 3 hours. That seemed really easy. This one also leaks memory, but yeah. So, and the reason I'm making these videos is because I am going to throw out the abstract syntax tree and just sort of make it a stack machine directly, because I already have the operations loaded. So yeah, so the next video is going to be on building the abstract syntax tree and operator precedence.